Hello students, my name is Sumit Sagar Hota. I am a PMR, a PhD student at IIT Palakkad. Today we will discuss the summary section for the week 12 and some of the MCQs also from the old sections. Okay, some of the problems actually left from the week 12, that also I will now cover by Professor Ashok Desai, IIT Kanpur, of the subject Introduction to Airbreathing and Propulsion. This is the extra live section discussion or the summary section. Okay. So let's start the section. Okay, so the first question is the reaction turbine is also called as dash. Okay, so the reaction turbine is also called as Propulsion turbine. Okay, invented by Propulsion. Okay, then compounding is used for dash power application. Okay, compounding always applicable for what? High power requirement. Where there is high power requirement, there only we will go for what? Compounding. In velocity compounded turbines, flow passage is from dash. Okay. Okay, so here for this question, there is no option suitable for that answer. Okay, so the answer will be the fixed blade to the multiple rows of moving blade with alternating fixed blades. Okay, so this is the correct option. Okay, which is not available. So I'll also write down the correct one. Okay, so yeah, a velocity compounded impulse turbine is also called like this. This is called Curtis wheel, invented by Curtis. Okay. Okay, invented by Curtis. Okay. Okay, so yeah, the turbine comprising of fixed blades and moving blades is called as a reaction turbines. Okay, this is actually a true statement. Okay, so the losses occurred while passing through blades are called as dash. Okay. The losses occur while passing through the blades. Okay, the blades, whatever the loss is there, that's always a what? Frictional loss. Okay. For mixing blades and rotating components together, dash are used. Okay, we call this is a new term called glands. Okay, GLNDS, glands. Okay. The losses occurred at gap between the glands are called as what? So this is a simple term, gland losses. Okay. The kinetic energy that steam has while coming out of the turbine is called as what? Whatever the things left, whatever the things come out from the turbine, that's actually left over. So that's the reason we called it residual. Okay, and the loss included with that is called residual losses. Okay. Okay. So now the problem started. Okay. So the first problem is a single stage axial flow turbine operates with an inlet temperature of 1100 Kelvin and a total pressure of 3.4 bar. The total temperature drop across the stage is 144 Kelvin and the isentropic efficiency of the turbine is 0.9. The mean blade speed is 298 meter per second and the flow coefficient is 0.95. The turbine operates with a rotational speed of 12,000 rpm. If the convergent nozzle is operating under choked condition, determine the blade loading coefficient, pressure ratio of the stage and flow angles. So let's start. Okay, so first start the blade loading coefficient. Okay, the blade loading is defined as what? So the next bit is, so first bit answer over. Next bit is what? They asked pressure ratio of the stage and stage. Okay, pressure ratio of the stage. So first of all, I will need to find out the temperatures, especially stagnation temperatures. T02 equal to T01 is equal to 1100 Kelvin. Sorry, not stagnation, it's the inlet temperature. Okay, so next T03 is equal to T01 minus delta T0 is equal to 1100 minus 144 956 Kelvin. Okay, and we need to find out the isentropic efficiency of the turbine. Okay, T01, T03, yes. To solve it, we will get the value was 0.533. Then pressure ratio of the turbine per stage or turbine stages. Okay, okay, this is what they asked. Okay, pressure ratio of the turbine per stage. Okay, so from here actually you can calculate the P03. From the two above equations you can calculate the P03. Because P01 already known. Okay. Okay, P01 given what? 1100 Kelvin and the total pressure is 3.4 bar given. Okay, okay, okay. Okay. Nozzle. Then when the nozzle is choked, okay. That means let the exit Mach number be what? 1. Okay. So the C2 is square root of gamma R T2. Okay. Now T02 by T2, and T02 is your 1100 Kelvin, is equal to gamma plus 1 by 2 is equal to 1.165. Okay. So now the static temperature at the nozzle exit is 944.2 Kelvin. Okay, so now what is C2? C2 is just 6. Okay, so similarly you can find out C2 square root of gamma T2. Okay, it's 600.3 meter per second. Okay. Okay, axial velocity. What is the axial velocity? Axial velocity is equal to CA, that's equal to U into phi, that's equal to 298 into 0.95. Okay, so what is the CA? Axial velocity equal to 283 meter per second. Okay. Okay, so now from the we have to actually take the velocity triangle. Okay, and that I already done in many times in the previous section, and you can see here also actually velocity triangle given in the 3 point. Okay, 3 and 2, the velocity triangles are clear. Okay, cos alpha 2 is equal to CA by C2. Okay, if you see here the alpha 2, okay, cos alpha 2 is equal to what? cos alpha 2 you can find into, okay, is equal to your axial velocity, okay, divided by c2. Okay, c2 is your what, diagonal. Okay, okay. So which is equal to 283 by 600 is equal to 0.4716, and alpha 2 is equal to 62 degree. This is your answer. Okay. In the similar way I have to find out also beta 2. I have to go u by c is equal to tan phi 2 minus tan beta 2 is equal to tan alpha 2 divided by 1 by 5. Turbine specific work. Okay, so now I have to find out the turbine specific work. Okay, because from there only I can find out alpha 3 and beta 3. Okay, okay. Okay, so now we have to find out tan alpha 3 because everything we know. Okay, so just now take the tan inverse and find out the alpha 3. Okay, so this is equal to 1.132, implies beta 3 is equal to 48.54 degree. Okay, the multi-stage axial turbine. Okay, so we now go for the next question. A multi-stage axial turbine is to be, just 1 second. Okay, so this is the question number 11. Okay, so a multi-stage axial turbine is to be designed with impulse stage and is to operate with an inlet pressure and temperature of 6 bar and 900 Kelvin and outlet pressure of 1 bar. The isentropic efficiency of the turbine is 85%. All the stages are to have a nozzle outlet angle of 75 degree and the equal inlet and outlet rotor blade angles. Mean blade speed is 250 meter per second and the axial velocity is 150 meter per second and is a constant across the turbine. Estimate the number of stages required for this turbine. Okay. This is the last question of the section. Okay. So then first we have to find out the overall pressure ratio. Which is a known quantity. Okay. Then go for this. Okay. Okay. So overall pressure ratio known T naught 1 by T naught ES is your P naught 1 by P naught E. Okay, so your gamma minus 1 by gamma is equal to 6 to the power 0.33 divided by 1.33. T naught ES is equal to 576.9 Kelvin. Okay. Okay, then our delta T naught overall we just need to find out. Okay. Oh, okay. So from the velocity triangle, C2 is equal to CA by cos alpha 2, that's equal to 150 divided by cos 75. Okay, so C2 is equal to 579.5 meter per second. Okay. Okay, then T naught 2 is equal to T naught 1 minus C2 square divided by 2CP is equal to 900 minus 579.5 divided by 2 into 1148 square, 753.7 Kelvin. Okay. Problem is actually I don't care. For impulse turbine, degree of reaction Rx equal to what? 0. Okay. Okay, so now we have find out the T20 in 3. So next we can find out so we are actually finding out the tan beta 2, and from there we can calculate the beta 2 as 64.16 degree. Okay, okay, so next we will find out the what b2. So b2 is equal to ca by cos beta 2 is equal to 344.15 meter per second. Then v2 is equal to v3 is equal to c3, which is your what, constant axial velocity. Okay, okay, so which is t03 is equal to t2 plus c3 square divided by 2cp is equal to 753.7 plus 344.14 square 2 into 1148. T03 is equal to 805.28 Kelvin. Okay, so you find out the T3 temperature drop. Now you have to find out the temperature drop per stage. That means what, T01 minus T03. Okay, So GST. So 900 minus 805 minus 805.28. Which is your 94.7 Kelvin. Okay. So number of stages required for the turbine is what? Okay. Okay, this is the required thing. This is what asked in the question. Number of stages required for the turbine is, okay, is what? So delta T naught overall divided by T naught 1 minus T naught 3 is equal to 274.6 divided by 94.7, okay, which is 2.89, which is 3 stages. Okay. So thank you very much for attending the section. If you are watching the recording one, also thank you very much. If you have any doubt regarding this extra section or any of the section, you can ask in the comment section in my YouTube channel Sumit Sagar Hota, in their respective lectures, live discussion sections. Okay, so this is the end lecture. This is the last lecture of the section. Okay, so thank you very much. Have a nice day. Good night and happy learning.